Hello. As a part of the series of video lectures that explain instruction set of the ARM processor, this current lecture explains in details the data processing instructions of the processor. Data processing instructions. These are the instructions which are used to process the data. The first type under this is the instructions for data movement between registers. These instructions move the data between registers of the register file. Actually, this seems to be a data transfer operation, but in ARM this operation is considered under data processing type. Only when the data is moved between CPU registers and memory, then it is called as data transfer operation, and those are that operation is handled by load and store type of instructions. But when the data is moved between two registers of the register bank, then it is considered under data processing type of operation. The instruction, let us consider the instruction move RD comma operand 2. So RD is the destination register. Operand 2 may be a register, it may be a shifted register, or it may be an immediate number. The register may be shifted by using barrel shifter, or it can be an immediate number also. This instruction will copy the operand 2 into the destination register RD. So these are some examples. RD may be any one of the registers of the register bank, and operand 2, as we have seen, may be a register, it may be a shifted register, shifted by using the barrel shifter, or it may be an immediate number, it may be an immediate number or a shifted immediate number. So for example, in this instruction, for example, move R3 comma R2 LSR hash 4. In this instruction, the content of register R2 is shifted right, logically shifted to right by 4-bit positions, and then it is moved to register R3. When a number is shifted to right by 4-bit position, then effectively we know that it is divided by 2 raised to 4, that is divided by 16, and then that result is moved to register R3. Similarly, for example, in this instruction, the immediate number 3CH is shifted left by 15-bit positions, and then the result is actually moved to R15. So that's how this instruction works. Other instruction under this category is move negative MVN RD comma operand 2. So this instruction moves the complement of operand 2 into the destination register RD. So these are the instructions for data movement within the registers of the register bank. Now one more thing to be discussed here is about the use of suffix s. Suffix s can be put to any of these registers, any of these instructions. When suffix s is put, then only that instruction affects the flags. Normally, in other microprocessors or microcontrollers, most of the data processing instructions, they affect the flag by default. But in ARM, the instruction, even though it's a data processing instruction, it may affect the flag or it may not affect the flags, and that depends upon the presence of suffix s in the instruction. For example, in this instruction, suffix s is not there, and therefore this instruction will not affect the flags. But if I put s after move, so it becomes MOVS RD comma operand 2, then that instruction will work in the similar manner, but it will affect the flags. So that's how suffix s can be used by the programmer in order to decide whether the instruction should affect the flags or not. Next type of data processing instructions are arithmetic instructions. Instructions are available for addition, subtraction and multiplication. So let us see the instructions for addition. Instruction is typically like this: add rd, rn, operand 2. So you can see that this is a 3 operand instruction. It will add the content of operand 2 to rn and the result will be stored in rd. Once again, operand 2, as we have seen before, it may be one of the registers of the register bank. It can be a register of the register bank shifted, logically shifted left or right by the barrel shifter, and or it can be an immediate number. These are some examples. We can see that rd and rn may be one of the registers of the register bank, and operand 2 can have different forms. It can be an immediate number, it can be a register, or it can be a shifted register. Okay, for example, if you consider this instruction, then it will add the content of R2 by the immediate number 40H and the result will be stored in R1. Okay, for example, here the content of R3 is logically shifted left by 2-bit positions, and then it is added to R2 and the result is stored in R0. It is possible that the destination register may be same as one of the source registers. Okay, so in this case you can see that R2 will be added to R3 and the result will be stored in R3. So these are some variations of addition type of instructions. Okay, next instruction for addition is addition with carry. It is identical with this, except that it also adds the carry bit to during the addition. Okay, and therefore in this case the instruction will work like this: it will add operand 2 to rn along with the carry bit and the result will be stored in the destination register rd. So these are the instructions for addition: addition without carry or addition with carry. Let's see the instructions for subtraction. Format is like this: subtract rd, rn, operand 2. Operand 2 is subtracted from rn and the result is stored in rd. There is an instruction which is subtraction with carry. Actually, this is the subtraction with borrow. Operation is similar to this, except that it also subtracts the carry bit which represents the borrow, and so effectively the subtraction is a subtraction with borrow. The operation is shown here. It subtracts operand 2 from rn along with the borrow and the result is stored in rd. Now here the borrow is not only the carry bit, but it is carry minus 1. That means if the carry bit is 1, then the actual borrow will be considered to be 0. 1 minus 1 is 0. And if the carry is 0, then this it is 0 minus 1, so only 1 will be subtracted from this. So in that case the borrow will be 1. So this is here, it is like this because the fact is like this. You know, when a subtraction is performed by an instruction, it is performed by using 2's complement method. The 2's complement of the operand 2 is added to rn and the result is stored in rd. So that is actually the subtraction. But in this type of operation, one additional step is normally taken, that is, when the 2's complement is added to rn, the result is stored in rd, but whatever is the carry, that carry is internally complemented. In all the microprocessors or many of the microprocessors like 8085, 8051, 86, the carry which is generated during the addition of this 2's complement to rn is internally complemented, because then it truly represents the borrow. See, for example, if operand 2 is larger than rn, then for this subtraction a borrow is needed. But when 2's complement of operand 2 is added to rn, in that case the generated carry is 0, and therefore when it is internally complemented, then that carry becomes 1, and then it truly represents the borrow which was required to perform this subtraction. So it means in the processors like 850 or 8086 or microcontroller 8051, the carry flag truly represents the borrow. But in ARM, this step of internal complementing of carry is not done. So in case of ARM processor, when this instruction is executed, only 2's complement of the operand 2 will be added to Rn, the result will be stored in Rd. But whatever carry is generated, it will not be internally complemented. It is not internally complemented. And therefore, the situation is exactly opposite. That means in this, when this instruction is executed, if carry is 1, then actually the borrow is not needed. And when carry is 0, it means that the borrow was needed. And that because of this change, that is taken into account by making by subtracting 1 from this. Okay, so this fact is taken into account while performing the subtraction with borrow like this. So you can understand that in the previous subtraction operation, suppose if the borrow was needed, then the carry flag will be 0. And then when this instruction works, because the carry flag is 0, 0 minus 1, so this minus 1, this 1 will be subtracted from this. Okay, because there was a borrow, 1 will be subtracted. But in the previous operation, if no borrow was needed, that means Rn is larger than operand 2, no borrow is needed, then in that case carry flag will be 1. And then when this instruction works, because carry flag is 1, 1 minus 1 will be 0, and nothing will be additionally subtracted during this operation. And therefore, when there is no borrow, nothing will be additionally subtracted. When there is borrow, 1 will be subtracted from this subtraction. Okay, so that's how this additional precaution is taken by this modified version of operation of this subtraction with carry. So in case of ARM, we can see that during subtraction, which is done by 2's complement method, the carry is not internally complemented during the operation of this instruction, and therefore the fact is that there will be no borrow if carry is set, and there will be a borrow. It means that borrow is required. Borrow was required when carry is reset. Now there are instructions available for reverse subtraction. Reverse subtraction RSB, RD, Rn, operand 2. This is similar to this, except the operands are reversed. That means here Rn is subtracted from operand 2 and the result is stored in Rd. Instead of operand 2 to be subtracting from Rn, it is Rn subtracted from operand 2 and the result is stored in Rd. That's all about reverse subtraction. And also there is a reverse subtraction with borrow. Again, it is similar to this, except the positions of these operands are reversed. For multiplication, multiplication instructions are made available due to existence of that multiply and accumulate unit in the ARM architecture. And therefore, there are certain restrictions on the operands. When you want to perform multiplication, there are certain restrictions. The restrictions are like this. All the operands should be registers. That means you cannot use immediate values or shifted registers in the multiply instruction. Okay, so in a multiply instruction, all the operands should be necessarily registers of the register bank. Secondly, RD and RA must be different. For example, in this kinds of multiply instruction, the source operands, RM and RS, and RD is the destination operand. It is required that the destination operand should be different from both the source operands. You cannot use the same operand here. RD should be different from the source operands. Third restriction is that R15, which is the program counter, cannot be the destination register in case of multiply operation. It means that during subtraction, in the subtraction and addition instructions, your R15 can be used as a destination register, which is not possible in multiplication. Okay, now there are two types of multiply instructions. One is called as normal multiply instructions and other is long multiply instructions. In the normal multiply instructions, the result is limited to 32-bit, and in long multiply instruction, the result can be 64-bit. So let us discuss the normal multiply instructions. The format of the instruction is typically like this: multiply RD, RM, RS. RM and RS are multiplied and the result is stored in RD. Because RM and RS are 32-bit registers, the product is typically going to be more than 32 bits. But this instruction doesn't allow that. It means that for this instruction, the numbers in RM and RS should be small enough such that the product will not exceed 32 bits. Even though the destination, that's how these operands should be small enough. Okay, then this instruction can be used. The result should not exceed 32 bits. Okay, this is the example. R4 and R5 are multiplied and the result will be stored in R3. Another instruction is multiply and accumulate instruction. It has 4 operands and its operation is typically like this. It multiplies RM and RS, adds this product to the third register Rn, and the result is finally stored in fourth register Rd. So this is a sort of instruction which allows you to perform, say, running totals. Price into the number of articles is added to the current total to obtain the final total. So that's type of running totals can be directly performed using this instruction. Multiply and accumulate instruction. So these both of them are normal multiply instructions. That means in both the cases the result cannot be more than 32 bits. Older versions of this ARM processor were having only this kind of multiply instructions, but the latest versions of ARM processor are also having long multiply instructions, in which the result can be up to 64-bit. That means a full size multiplication can be performed by using these instructions. Now under this, there are separate instructions for unsigned numbers and for signed numbers. In case of normal multiply instructions, multiplication of only unsigned numbers is possible. You cannot multiply signed numbers. But in this long multiply instructions, separate instructions are available for unsigned and separately additional instructions are available for signed numbers. Instructions for unsigned numbers: unsigned multiply long, unsigned MUL multiply long, and there is a list of 4 registers. Out of them, these two are the source operands, two 32-bit operands which will be multiplied, and these two are the destination registers. Okay, so there are two 32-bit registers named as RD higher, RD lower. So the 64-bit result will be stored in these two registers together. Okay, RM and RS are multiplied and the result will be stored in this pair of registers, lower part here, higher part here. So that's how this instruction works. Similarly, you have unsigned multiply long type of instruction. Once again, you can see that RM and RS will be multiplied. The product will be added to the current content of this pair of instructions, and again the result will be stored in the same pair of instructions. So this is multiply and accumulate type of instruction for unsigned numbers, and the result can be up to 64-bit. Similar instructions are available for signed numbers. Okay, these are identical with this, except these instructions, they consider these numbers operands, source operands, as signed numbers. Therefore, they take care of the sign of the result. Okay, now let's go to logic instructions. Under this, there are some basic instructions, that means the instructions for basic operations which are shown here. They perform basic logic operations, AND, OR, XOR. The instruction is shown here, AND RD, Rn, operand 2. Okay, so Rn and operand 2 are ANDed together and the result is stored in RD. Once again, we know that operand 2 may be a register, it may be a shifted register or an immediate number. Similarly, OR operation, similarly XOR operation. Now let us see this operation, which is or this instruction. It is bit clear instruction. Bit clear instruction. Bit clear RD, Rn, operand 2. This instruction is actually used to clear certain bits of Rn and store the result into RD. That can be achieved by putting an appropriate bit pattern as operand 2. In that bit pattern, you have to make those bits 1 which bits of Rn are to be cleared. Suppose bit D0 and D1 of Rn is required to be cleared, then in this bit pattern only bit D0 and D1 should be kept 1 and all the remaining bits should be kept 0, and then this instruction will clear those 2 bits of Rn and the result will be stored in RD. This instruction internally works by performing this operation. It actually performs AND operation between Rn and complement of operand 2. Okay, see the example. For example, bit clear R0, R1, #1010. This is the bit pattern as operand 2. Here we want to actually reset bit D1 and D3 of R1. So what will internally happen is like this. This is complemented. Okay, so when this number is complemented, all the bits except D1 and D3 will become 1. Right? When this is complemented, all the bits except D1 and D3 will become 1. And then that will be ANDed with R1. So when any bit of R1 is ANDed with 1, those bits will remain unchanged. But when any bit of R1 is ANDed with 0, those bits will reset. And therefore, in this instruction, only bit D1 and D3 of R1 will reset, and that pattern will be stored in R0. So that's how this instruction internally works by using by ANDing Rn with complement of operand 2. Compare and test type of instructions. In these instructions, suffix s is not needed. This is because these instructions, they give the result in the form of flags only. Okay, so when these instructions they work, the result is indicated in terms of setting of the flags, and therefore s is not needed. Even otherwise, these instructions will always affect the flags. In all the previous instructions, we have seen that if s is not put, then the instructions will work, but they will not affect the flags. If you want that the instruction should affect the flag, then s should be put as a suffix in the mnemonic. But these instructions, they don't need suffix s. They will always affect the flags because their output is in the form of flag settings itself. Okay, compare Rn, operand 2. It will simply compare these two operands and the result will be indicated in terms of the flags. Actually, this instruction internally works by subtracting operand 2 from Rn. You know, the result is not stored, but the flags are affected. So that's how this instruction works as usual. So for example, if operand 2 and Rn are equal, then when the subtraction is done, the result will be 0 and the 0 flag will set. So 0 flag is set indicates that the two operands are equal, like that. Another instruction available is compare negative, Rn comma operand 2. It compares negative of operand 2 with Rn. Negative of operand 2 with Rn. That's all. Otherwise, it is operation is similar to this. So it will subtract minus of operand 2 from Rn. The result will not be stored, but the flags will be affected, and that will indicate the comparison. The other type of instructions available here are test type of instructions. Test equivalence, TEQ, Rn comma operand 2. This instruction is used to test whether these two operands are equal or not equal. Internally, this instruction performs an XOR operation between these two operands. Once again, the result is not stored, but the flags are affected. For example, if the two numbers are same, they are equal, then 0 XOR 0 is 0 and 1 XOR 1 is 1. 1 XOR 1 is also 0. 0 XOR 0 is 0 and 1 XOR 1 is also 0. So when these two numbers are equal, then the result of this operation, XOR operation, will be 0 and the 0 flag will set. And therefore, when the 0 flag sets, it means that Rn is equal to operand 2. Okay, otherwise the 0 flag will reset. So that's how this can be used to test the equivalence between the two operands. This instruction is used to test the status of individual bits of Rn. Test bits. For example, if you want to know whether a certain bit of Rn is 1 or 0, then this instruction can be used. In that case, whichever bit you want to test, bit of Rn, that bit should be set in this pattern, and all the remaining bits should be kept 0. For example, if I want to test whether bit D1 of R0 is 0 or 1, then I have to give this instruction like this: test R0 comma this pattern in which only bit D1 is set. Okay, you want to test this bit of R0. This instruction will internally work by performing this operation. It simply performs an AND operation between Rn and operand 2. So when this is ANDed with this, once again the result is not stored, but the flags are affected. So when this is ANDed with this, you can see that all the bits except D1 bit of this register will be set to 0, and then bit D1 therefore will decide, bit D1 of this will decide whether the result is 0 or not. If the bit D1 of this is 0, then the result of this operation is 0. If the bit D1 of this register is 1, then the result of this operation is non-zero, and then the 0 flag will indicate whether the corresponding bit is 0 or not. Okay, so when the bit is 0, D1 bit, then the result will be 0, and in that case 0 flag will set. Okay, so if the 0 flag sets, it means that the D1 bit of this register is 0. So that's how we can test whether any one bit out of the 32 bits of this register, whether any one of the bit is 0 or 1. So that's a test bit type of instruction. So all these are coming under data processing instructions. Okay, we have seen under data processing instructions, we have seen that data movement, instructions for data movement between the registers. Then there are arithmetic instructions which include instructions for addition, subtraction, multiplication. Then logic instructions which include some instructions for basic logic operations. Then instructions for comparison and instructions for testing equivalence or testing the bits.